No, in the end of the lecture, I formulated actually one main idea about the molecules of algebra, and this idea actually was following. That, suppose some algebra A, and this is algebra. In our case, it was shuffled algebra. We have many different, several different shuffled algebra, and we can use them. And the situation when we can derive from algebra the object which let us call arithmetic is following. In general, it can happen, and it's really happening in our situation, that suppose in B we can find out some collection of subspace, V1, V2, and so on. No, actually it can be infinitely many. It is some just a collection of subspaces, and it is possible that the following situation will happen. That there are just subspaces in the algebra, and we can study their product. So product means that they are part of the algebra, and so the product means is going to the algebra. It is just the product of the element, and also with let us name I, so J and J times VI is going to be again, and the situation which we are talking about is the following. First, suppose that both these maps are embedding. This is the first condition. Second condition, suppose that the images of this map coincide. Yes. So if such situation happening, and this is not happening in this business, then it gives us a matrix VI times VJ to VJ times VI. No, this is just because the product is just the same space, and later, if it is just happening, let us call this permutation or arithmetic. Arithmetic is usually this times usual permutation. Anyway, it is, if such things are happening, that at least we get something, and then suppose that the third condition is true, and this third condition that if we have three different of them, VI times VJ times VT, yes, and then we can consider just product of them, how it is written. I mean, if we have V1 from here, V2 to here, V3 to here, and this is going to a product that is V1, V2 times V3. So it is also a map from this to B, and suppose this map is also embedded. if such situation is happening that we have family of some kind of, let us use this permutation, Rij, and if such things are happening, then such permutation Rij satisfies up to the fact that they are not hermetic, but are hermetic and permutation, they satisfy Young-Bart's equation. So such kind, if such kind of situation occurs, name of this that we have homological algebra, and what I tried, maybe a little bit unsuccessfully, to explain that at least I formulated the usual hermetic. Usual, I mean that when what we can find and hermetic, which is connected with quantum group of type of linear streams, for example, or some similar examples, they can be constructed by this. And our case, which we're discussing, is actually very close to this, and it gives us actually the same situation. And no, a little bit later I recall, or maybe recall, I just formulate how such kind of structure, such kind of picture is used for construction of integrable systems, the system of commuting operators. But just now I want to say that we have such picture, and then what was the shuffle construction of yesterday lecture? I will say actually the same thing, but I generalize a little bit and also slightly change the notation. But well, so we worked always with C star and function on C star. So the object in our shuffle algebra will be function, symmetric function with some properties, poles maybe, and so on, with real conditions on C star times C star. Yes. Now let us construct a little bit bigger shuffle algebra, but let me do the following. I want to replace C star just at one point. So now my space where functions are leaving a little bit bigger. C star plus 1 point, which is just disjoint union to C star. Yes, and so construction of shuffle algebra, it is always the same. Construction of shuffle algebra, I recall, for shuffle algebra we need some set S and some function lambda in 2 variables, and S1 and S2, and then we write this star product and get the algebra. Now S is C star plus 1 point, and we need function on S times S. Well, what will be our notation? Z is point here, and maybe P with some of this extra one. Well, and now function lambda E1, E2 is the same. It is our standard function with 3 shift Q. And in principle, I can maybe let me formulate it in general now, but I want, I also need lambda t. In principle, it will be 1, and lambda that p it is the function. Yesterday it was in a similar thing. It was the function e minus k times e minus y. Yes, and and yesterday it was function lambda t z.
Y is p, huh? Y is p.
No, p is no. Yesterday it was in my notation. It was some confusion. P is extrapoles to this. Y here is parameter. It is number. And k is number. Yes. And no, it is just some function depending on p is fixed. And this can be some different things, maybe 1. Or here I can have in principle more complicated objects. Just I can take some rational function in one variable z. Usually, because of some technical reason, I want equal number of things in numerator and denominator, but in principle, it is not important. Well, and after that, again, it was a part of yesterday's discussion. The corresponding shuffle algebra now this actually it is by grading, but this shuffle it has grade, natural grading, such that in grading 0 we have our previous shuffle algebra, which does depend only on z. So it is just functions which are 0 one variable is p. So in degree 0 we have also no because our set is union of this and this, so then the symmetric function on this set is what? This is just symmetric power of as a set. What is this? If I put A, this is just symmetric power, the area of star plus A minus 1 of star. It means 1p here. Then A minus 2 and so on. Then, how many p I have in this symmetric power, and so this is in grading 0, and this is in grading 1, this is in grading 2, and so on. Anyway, in grading 0, according to this notation and this explanation, we have our initial shuffled algebra, and this is again what I explained yesterday. We have actually in a grading 1. And in a grading 1, yesterday our function was this, and And I said that in grading 1, what actually we have? We have the object which consists in function, also in the1 and so on. The n, no, maybe the l minus 1 or the l, it's just this, what we have here. 1p and all others are z. It is here. But what functions we have to put in this place? Now, general strategy, we need some rational function, and we want this rational function, we want restriction of order of a proof, and also we want some kind of real condition, and all of them have to be here. And this I formulated, and in this one, what we have, this is possible to write here. F is what? F is some polynomial, symmetric polynomial, P1 and so on to the yes, and no, we have summation in L, it is also created space. Some I am talking about H component. It is this, and here we have as usual the product, the I minus V square. Yes, and here I have the product, the I minus Y, which is because of this. And about P, it satisfies real condition. And yes, and so this will condition, let me not to repeat, but for example, if he is generic, then real conditions are only here. So this is our old real condition which we had before. Yes. If K is some special, then we have extra condition which appear no, more or less as I explained, let me not to repeat it. Anyway, here we have no, in degree 0 we have our old shuffle. Let's denote it by H0, and here we have some new space which let me denote it by shuffle 1. So it is all, no, it is similar object to functions, but some additional properties. So it has pulls here and maybe some extra condition. Anyway, this shuffle 1 is bimodal with respect to the action of H0. So, and by the way, the structure of this bimodal, no, it's clear from definition. From one side, I take this function and just calculate the usual shuffle product from the right, from the left. And from the right, in the formula for shuffle product, this function involved. Yes. No, it is simple. It can be formulated by any way, many ways. It means that on all space of functions, let us not specify their properties. We have action from the left and action from the right. And what we are doing here, from the left we do not change, from the right we conjugate it to this function. And it gives us the action, the bimodal structures here. Yes. And let me formulate this, first of all, the proposition, a theorem, I do not know what. Okay, so let us take this bimodal, shuffle 1, and suppose the case is generic, and I can make the procedure which I explained yesterday. Which one? I can take shuffle 1 and factorize it by the action of shuffle 0, say from the, maybe from the left. Now what does it mean? I add this part to this part. First of all, I'm acting from the right, and then I'm acting by elements of degree bigger than 0. So I'm not acting by 1, but I'm acting by generators, quadratic things, and so on. And after such factorization, we get, I factorize from the left, I get right model. With respect to shuffle 0. And this right model coincides with Mark-Margone representation, which I introduced before. It is just, actually, it's just more or less the same construction, but reformulated a little bit. Yes. And if K is and how it is happening, again, you see that our space is looking more or less by the same as the shuffle, but it has poles. If you're factorized by the action from the left, then more or less all disappear and only polar terms remaining after this factorization. This is more or less clear on the first level, but similar things is happening further, and this is what is going on. So bimodal is this. So next part of the construction, get the construction in order to get this one was following. Let us take this shuffle 1 again. So maybe I did not say it clearly. This shuffle 1 is the space. I can't make it special space of function. We can say this satisfies real condition. Yes, and then maybe the problem which I'm talking now, I get the representation of shuffle by factorization of subspace like this. But next step will be the following. Let us construct the, let me put here notation regular, and yesterday I used the notation subspace. It is a regular subspace, and what is this? And my definition was the following yesterday. I consider not all functions which I have here, but functions which have some regular properties. And these regular properties were following, that such functions have full only in prescribed space, in the place. So if the I equal y, it is full. And also if the I equals the j, full, and no poles in other places. And it is one thing, and part of this regularity condition that f also regular, better to say it by the following way. F regular in 0 and infinity. By this way, my definition of regularity is always the same. And let me recall, I just put in function z some epsilon vs, epsilon vs plus 1, and so on, epsilon v8, and I fix this element, send epsilon to infinity to 0. And it has some condition in infinity to 0, and by the way, yesterday I said that this condition that limit in 0 is finite, limit in infinity is 0. Yes, but the definition of
S is fixed or S may be different.
Different, any.
So many limits.
No, I can, if function depending in 5 variables, then I can take one z and fix all others and send it z to 0 and infinity, or I fix 3 and take 2 to 0 to infinity, or simultaneously. Yes. And such kind of regularity, by the way, can be varied. For example, I can replace this by condition that limit in infinity is the same as limit in 0. Or the ratio is just something now. This is also possible. Anyway, we will work with this, but here I only want to say that we have some freedom in this regularity condition, and well, it is some subspace, and if I like to use the language of the generate elliptic curve and things like that, and from this algebraic point of view, it just means that I'm looking functions which are regular up to admitted pools on some kind of degenerated elliptic curves and things like that. Anyway, this is some regular subspace, and now the important fact that in my space shuffle 1 I have two subspaces. One subspace is shuffle 1 regular, is a subspace. And second subspace is this. And the fact is that this is complement to this. Actually, our shuffle 1 is the sum of shuffle 1 regular plus this subspace. This subspace is the result of the action from the left. Shuffle 0, let me just rewrite. No, anyway, actually it is some conceptual things, but I cannot explain it. It can be proved, and it is not evident at all. But I cannot explain, unfortunately, now why it is happening. Anyway, if you look on this space regular, so because of this, you can identify this space with this quotient. And for example, it means that on this space, on this regular space, we can construct the action of our shuffle algebra because of this identification, and just on space of regular functions as they are, such kind of action is not evident also. But this regular subspace is good for definition of hermetic. And let me explain what is going and how it is possible. So for constructing of hermetic, let us do the following. Suppose we have, anyway, my construction of space shuffle 1 and shuffle 1 regular depend on the point, no, this is the point T, which we add. And now let us do the following. I want to consider at F bigger space than here. I want to take C star and add 2 points, P1 and also P2. Yes, and now on this bigger space, if I want to determine the shuffle algebra, I need here function lambda, and as before, what I actually need function in V1, V2 is the same as before, function lambda in V1 and P will be Z minus K times V minus Y, and maybe opposite is 1, and here is P1. And lambda V2 is, and let me put here 2, here let me put integers here, and here is V minus Q2 divided to V minus Y2. And in principle, I need more of something lambda P1, P2, but maybe we need some change, but maybe suppose it will be 1. Now, in inside this bigger algebra, which we have here, by a similar way as I explained before, we have this shuffle 1, E1, it is where E2 is not involved. And we have shuffle 1, E2. And we have such space, and because we live in the algebra, we can consider product. We can do product, it means I can take functions. Here I have on this part, and I can take function on this part, and just calculate the product in the whole algebra. Again, in all time I'm using the same star product for yes, and then if you calculate such product, then you go to something which we can denote maybe like this. Again, this object is functions j in v1, vn. No, with some properties again, which can be easily formulated. Again, properties are always the same. That real conditions, and in this case, they will have both in y1 and y2, for example, function which are here. And then, so we have a product from this to this. Yes. And then it is the interesting things are happening. If I put regular here, and I go to regular here, and the fact is that the condition what I need for this homological business is true. So here, a part of this homological business which we need, I want this map to be isomorphic. And this is just a fact. Yes, and well, if you want to use it, no, you can easily predict what I want to say, that all things what in principle we need for this homological algebra are true here. No, for next condition, it means we need a little bit more. We need third point, and then shuffle 1 or 3, and also regular here, and then I can calculate their product in this order, and again I get some collection of functions. And their method. Well, and again, so in this case, if I have one, I'm saying that what? Their construction depending surely in I1, which is not very important. No, it is important surely in this K1 here. And then, no, if you are considering this just a regular space, so first you have to look what is it. And again, if you are doing with this function, especially with a regular condition, if you want to count how many, then we can use this Gordon filtration business. And this is the only way to work with this complicated well condition and so on. But Gordon filtration business helps us, and we can find the Gilbert series of these. And it is in correspondence what I said there. So we saw, for example, here that in the lowest level I have 1. On the next level I have only the function 1, v minus y1. It is only 1 here, and this is in a regular space only this function survives. If you consider functions in 2 variables, then again you count number of the function by the same way, and you find that you have 3 such functions and so on. And so this calculation really gives you that this space itself has Gilbert series like this Mach-Magon plane partition. And this is the same. No, I said that actually this calculation I explained something before, and I said that this is the same thing. But we can find on the character level, first of all, that what is happening here has the same sign. And really the character will be 1 minus 1 minus u, 1 minus u squared square, and so on. And by the way, I can no possibility to explain details, but very interesting things are happening. That I explained that if K is special, then extra will condition. We add them, and then the space of this regular function becomes smaller. And how much smaller we can see in principle. And as I said, that for generic K, this space has natural. In this notation is not very natural. It has some basis. In this description, we still no basis here, but at least I explained that before it was basis labeled by plane partition. If K satisfies some resonance conditions, we have to kick out some plane partitions, and the basis does become smaller than that. Anyway, for special K, we can get different type of representation and block representation. There is an example of that. Maybe I explain something. Maybe not, it depends on the time, but how it is happening. Well, if you are talking about, for example, tensor project of tubes, then well, this is also very explicit description of this space of functions. Still suppose 2K, K1 and K2 are generic. Then, for example, on the first level, now we'll have function with poles in y1 and y2, and there are 2 such. That's it. On level 1, on this tensor project, I have this function, and I have this function, and any function in this regular space it will be a combination of these 2. I have 2, and also if you have tensor project of 2, if you not tensor project, but better to say what 2 belong to 2. Yes. Then again, in this case, you also examine this space with help of Gordon filtration, and you see that the character is just a product of 2 Mach-Magon characters. And in this case, it's the product of 3 Mach-Magon characters, and so it is like no, we can play, should and generalize it by many ways, even in this case. We can, as I said here, we can consider the smaller space where K is special. Or we can consider the big number, more complicated rational functions here. So basically, the situation will be the same. no, by the way, to be honest, that no, the fact that really we get arithmetic or the homologic algebra by this construction. In general, I do not know if so.
What is spectral parameter? It is constant.
No, spectral parameter is given here. Y1 is spectral parameter, Y. So this space, depending in T, but real dependence in Y. T, so this object is here, it play a role, and really this is height weight. And this height weight knows the spectral parameter also. And in standard language, this is level. Now, in representation, this is level. So I have not a language for that, but level is how central elements of some algebra is actually there. We do not have the full algebra, we have only one half. But the meaning is this. Now let me explain how arithmetic usually use it. So this is a general thing. Suppose we return to very general situation where we have a collection of spaces V and such kind of permutation relations, then in this case, this is a way to say the following. It is so-called the conception of area operator. No, the conception of area operator, this is the following. Let us take any space from this, say Vn. And because it is some, we have a map. And the operators, they are matrix elements of this map. So what does it mean? I can take element I from V1 and element beta check maybe from V1 star. And then I can take element W from here times alpha. Then apply this R, and this pair is this beta check. No, because this is here. If I pair it with beta check, I go to this. And this is the standard definition of area operator. And this L operator denoted by I. Beta check, and this is acting from Vn to Vn. It is always interesting that it means that I take this Vn, and on Vn, no, this construction says us that it is a map from V1 tensor V1 star to endomorphism of this space. And this is main idea of this operator business. So it means that each space from this Vn, we have Vn. On Vn, we have the action of a lot of operators, and And these operators, they satisfy relations. Some of them, many quadratic relations of them, are usually calling relation follow this Leningrad notation. And no, I skip some technical details because in general we need some. No, in general it is not enough. But anyway, but on naive level, it means that just from this on we have the action of some else. And by the way, this is really how quantum group was discovered. Quantum group was discovered from somewhere people knew permutation relation. After that, they write such kinds of L operators, and after that they saw that by this way they get some algebra. And this was the first. No, actually this is the main example of quantum group because this algebra has also co-multiplication. Well, and it is such kind of construction can be applied in many cases, and in our case also. Well, so to what we have? We have a family, if we are talking only about this, we have a family of spaces, which is a regular space, which is one, and P is really they depend in parameters C and Y. Yes, and then we can take such space, and because of this we have hermetic, therefore each of these spaces is a representation of some algebra. And for example, it is possible to solve the following problem. Suppose I explain that each of these spaces also can be understood as a quotient of bimodal up to right x or left x or and right also. But so in this space we have the action of our shuffle algebra, and the question is how it's related with such kinds of constructions. The answer is no. I can answer only positive, related. It is possible to express one action through other action. How? Maybe it is not possible to explain now. No, it is one. And other things that in principle, if you are talking about equilibrium, homology of Gilbert scheme and so on, then this is the space where we have the action of this algebra, and we have dual actions, the joint one. And altogether, they give us the representation, what people sometimes call it the action of toroidal algebra, and such action can be constructed by this way. Now, let us move to the direction to integrable systems. notation are not so good, but let me put here x and y. And as I said, this space is representation. Anyway, the character of this space is given by Mathematical point. Yes. And as I said, we have maybe I put here some K prime and U here, and it is permutation. Now, using this as operator formalism, so I can take this and this, and take vector here, and take co-vectors here, and get some operators which are acting here. For example, let us, from in this space, no, basically this is the same space, and we constructed it explicitly, and it has vacuum vector, and just one from this space. And here we have also vacuum vector or vacuum covector. So I can take this L operator. I want to know the vacuum vector here. Now, usual notation is following. This vacuum vector usually denoted by empty, because as plain partition, no box. And so covector is same, and this operator depending in U. And it is standard thing that just from Young-Baxter equation, it is following that this operator is empty U1 and is empty U2 is 0. And so it means that by this way we get some commutative algebra of operators which are acting on this space. Or no, we have more possibilities of constructing the commutative algebra. And one possibility is following, that, well, let us choose here in this space some base. And this base is, if K, no, this representation in principle can be any choice, and we can have this real condition or not. Suppose not. So in this space we have a base which labeled by some plain partition, say yi. Yes. And then we can write down that trace type operator. Namely, I can write down the sum, and in the dual space, let us choose the dual by space. Then we can write down, and people are always doing like this. We can take this L operator here, a alpha, y alpha, here y alpha check, and here P. This is number of boxes in this young diagram, all level. And no, this is infinite sum, but if P is small, then this operator converge. And then it gives up to us some operator depending in parameter P and U also. So let us denote such operator. Let me just put this parameter P here. P is standard notation, and I use P for a point, but now it is just parameter. Yes. Anyway, we get some operators depending in P, and U is here because depending in P here. And the fact is, again, immediate consequence from Young-Baxter equation that such operators are commute. And
P appears.
where?
In commutation relation.
So here?
Yeah.
No, they have to be equal.
Yeah.
No, if not, then nothing like that. If they are equal, then they can be. No, well, so we have some family of integrable systems depending in P. And no, in this special case for such integrable systems, there are rather interesting formulas. Maybe I'll explain something closer to the end of my lecture. But it's many reasons to like such kind of operators. One reason is following, that, no, first of all, if I cannot say much about geometry, but what I said, that here we have a collection of representations of, no, this is representation of algebra or collection of spaces that this is a vector, maybe depending on phi and y. No, just this representation, again, so if K is special, then we can construct the fork representation and identify it with some geometric objects with the sum of equivariant K0 of given. If we change construction a little bit, that this algebra has other type of representation, which are related by the same way with equivariant K0 of given. Now, if you ask me about geometric meaning of just this representation, where bases explain partitions and things like that, then I do not know. It has to be some geometric meaning of this, but how to do it, I do not know. Anyway, if we have, for example, Gilbert schemes of G points on a plane and take equivariant K theory, and on this equivariant and take the direct sum in D. That anyway, I said that it gives us the example of representation of this algebra. Yes, and on each space we have each space is equivalent K-series, so it means it has a structure of commutative algebra. So it means that the product of the elements gives us the action of some operator on a representation, and so from geometrical point of view, it means that we have integrable system. And this is McDonald's integrable system. And if we here conjecturally, maybe now not conjecturally, we have quantum equivalent K-theory, and so we have some additional parameters which people usually denote by P. But actually it is the same space. So we have a family of some operators which are acting there. And it gives me a family of integrable systems depending in P. And it is, no, I think it is Ullmann's theorem, but maybe not precise. That this integrable system coincide with integrable systems we construct by this way. It is definitely theorem which we are talking about equivalent homology. And if we are talking about P-theory, that may be not. So, from geometric point of view is what? That we have some kind of instanton manifolds where by this way some commutative algebra are acting, and we want to say something about the action of this commutative algebra. And this commutative algebra, they have eigenvector, eigenvalues, and so on, and the problem is how to determine. No, this is from point of view of geometry, but return from the geometry to our shuffle business. So, well, what was our construction? Well, so first the construction was what? So we, let us return to the beginning. So it was union of, now P is a point, yes, and we have this shuffle one, so its function and variables with some properties, and as I'm saying that this is bimodal. Yes, and so, but again, it is some this regularity business, but let us look first who else is acting on this space. It is bimodal, yes, but here we have the action of Cartan, which I mentioned. So it means that I can take element hi, and this hi is acting on a space of any space function of n variable by simple way. It takes such function f, v1, vn, and send it to the sum of vi, maybe to the m here, vi power m, Newton's polynomial times f E1 and so on here. So we see that we have on the whole space here, we have the action of rather simple commutative algebra, which is this. And I erased, but what we first did with this shuffle one space, I skipped this P, we took the quotient by the left action. It was shuffled 0. No, this is the space which I said we have left action. First of all, but you see that this subspace is invariant with respect to the action of operators Hm. Therefore, on equation, we have the action of operators, just operators Hi, and and it gives us on equation the action of some commutative algebra. And I also said that this quotient is isomorphic to a regular part of this. And on this regular part, I have the action of this L operator and empty check depending in U commutative algebra. And the fact is that this commutative algebra and commutative algebra which is generated by Hm is the same. So these operators, which we have here, from the they are rather simple, and just product to Newton polynomials on this quotient, or if we can rewrite this here, then it gives us the action of operators which in a special case coincide with McDonald's operator. Yes, and by the way, if on the space of this regular function you want to calculate the action of Hm, that it is not very simple business, because you have to take regular function, then product to this regularity condition now disappears, and then you have to project it back. And so from the point of view of this regular function description, action of this Hm is something non-trivial. Yes. Anyway, right now we have that the action of Hm gives us the commutative algebra acting here, and again, from a geometric point of view, by this way we get just the product on a case here. So it means that each Hm goes to some explicit covariant shift or element of case theory on the Hilbert scheme, for example, and this is product 3. Now about what we will call P deformation. Then how to describe? No, because of some. No, it is strange, but it is possible to change a little bit this part of the story. So what is written here? I factorize by what? It is enough to factorize by the following. I have function with p1, and minus 1, which is from here, and I can take from this the element of degree 1, so I can take j v 0 state and to take start product, and so we get some amount of function which are here, and we have to factorize by them. And such kind of factorization things, it is very easy to change a little bit by the following. Let us factorize not by that, but by function j f minus f times times p. Let us take not the quotient from the right, but a sort of p bracket. It can be reformulated by many ways, and more mathematical one, but actually we are doing this. So what does it mean? It is not evident, but if I make the quotient by this, we have some subspace here. But now this subspace deformed, depending on p. So we have some, for p equals 0, we have just this. For generic p, we have subspace like this. All kinds of elements of such sort, and we span subspace by this, and it gives me something here. Let us denote it by some way. Maybe let us put here. And then not evident, but not very complicated fact that we have a family of subspaces, and this space depending on p. And this is flat deformation. And so the quotient is also family of spaces depending on p, and this is also flat deformation. This is one thing. Other things which I want to say, that I said that operator Hm preserve this subspace when p is 0, but it also preserves this space when n. No, it is again because of the structure of this product. No, because no, the simplest way to see is just look to the formula, but it's also some simple argument about this. Anyway, the result of such things gives us the fact that we have a family of space depending in P. Yes, and this is flat family of spaces, and operator Hm are acting there. And this is surely be commutative algebra. And if you want to write, to get from this integrable system, it is possible to do the following. What is our situation? So I have this H1, we have some subspace H1 regular is here, and I have complement. That in complement is some subspace depending in C, complemented is this. Yes, and so if I want to write, it's a little bit non-precise, but nevertheless, I can take element W from this, then it is a regular element, then X by HM. It gives me some element from here, which is surely non-regular, but after that project it back along this subspace. And it gives me some operator acting here. So we get family of operators labeled by M acting here, depending in, and construction is because of more or less evident reason give us commuting family of operators acting on this regular space. No, the interesting things and not completely understood, maybe from more or less because from technical level, but it is true that on the same space, I mean in this space, we have the two different constructions of commutative algebras. One construction, this is because of this hermetics, of this homological business. I take this regular space, I have other regular space, and then I write down this complicated sum, this L operator element depending in P, and I get some element from some commutative algebra, and again the commutativity follows from Young's bucket. And from the first glance, this is a completely different way to get commutative algebra on the same space, also depending in P. And the fact is that this commutative algebra actually coincides. Now, these elements belong to the same commutative algebra. Well, now I always thought, by the way, that in this construction, it is very simple way to deform the commutative algebra. And no, because also it is quantum multiplications and so on, and we want to connect this with this, it has to be some good way to do it, and how, for me, it's a big question. But, this construction of integrable system and what people are calling Bethe equation, this is actually the same. And let me explain why. So again, this subspace, this P, it was here, and what was it? I take function G, Z, 1 times some function in maybe Z1 to Z8 minus T product in opposite direction. We have F1 so on Z8 and here J. Yes, and no, well, the product is following that I have this, I have to write down like this and put here. Anyway, I have to calculate this minus this. And But let us look. What is written here? Here, when I calculate this, it is what? It is G E0 times F E1 and so on E8. And here we have product of this function lambda E0 E8. And then we have to symmetrize. And then minus what? Minus what is written here. Then we have parameter p also some symmetrization here, but we have f this is here from that part. Here we have f E0 E8. Here a minus 1. Here G E8. Here we have a product of lambda Vi. And here we have also additional product. And this additional product, because actually we have P somewhere. So we have a product. In our case, it is a product, if I write it correctly, the I minus K, the I minus Y, I is from 1 to n minus 1. I think it's correct. 1, this minus this, it is just what is written here. Then, and what we want to know? We want to know what is this. And and what is Bethe equation? Bethe equation that says as the following, that we want to find the set of V1, V0, and so on, V8, where this difference is always 0. Now I subtract this with this. From this I subtract this. And what we have? This is symmetrization. And in this symmetrization, because the function is symmetric in A, we have A term. For example, one term is just this. It is J V0 times F V1 V8 times the product which we have here. Yes, and yes, and a similar term we have here. And similar term, I make symmetrization of this, and I'm interested in a case when after symmetrization I have to put the zeros here, in this place. So here we have a term after symmetrization which this is the same thing. So it is F E1 8 minus 1. Here is 0. And here it will be some product. No, we have to put 0 on this place and 8 here. Yes. Then they have to be equal. So if we have some product, and here we have product of these things minus product of these things times p. And suppose Z is some set of points where it is 0. What we need for that? Let us look at. I have this difference is 0 on a set of points if the following is true, up to if for any I, it is what? V I minus K over V I minus Y, here product lambda V I J, J have to be equal. No, I confuse where is P, unfortunately. But up to this confusion, it is what? It is G lambda V J V I. Yes. Maybe I write something incorrect in this formula. Anyway, if you write it correctly, just start product from the right and from the left. And consider, suppose we want this be 0. So again, it is, no, it was correct all the time. What I do? I take G times F. Here in one variable, here in 8 minus 1. And also again the same, one variable and 8 minus 1. By this way, I want this minus p equals this, b equals 0. Then my problem is following. That I want to find E1 and so on E8 such that I expect that this minus p times this is 0. So what actually I did, let me just repeat in words. I write down the shuffle product for this and write down shuffle product for this. And here I have n term, a term, and here I have a term because of symmetrization. Yes, and each term, each term is looking the following here, for example. So it is, in my notation, it was like this. Anyway, each term is looking like the following. It is G, Gi, F, G0, G minus 1 without Gi. And here it is some function here. The shuffle formula is the sum of such products with the coefficient here. And if I write down this term, it will be a similar thing. We will have sum of such things, G of Gi times F, and here it will be also some product of functions. And we want subtract this with, I want this equal to this times pi for any G and F. For this I need that these two products of factors differ by p. And this is just what is written here. No, excuse me, unfortunately, what I wrote before, maybe it was incorrect, but, or not precisely correct, but the result will be this. So, again, what actually is happening here? We have p brackets here, and there are some symmetric functions, say in a variables in some degree, and if we choose, so here this is collection of equations. So for each choice of I, for each choice of this I, we have such equation. And well, we have a variable and a equation of such sort. Suppose that the E0 and E minus 1 is some solution. If it is solution, so it means that the function which we have here are 0 on this set of z. So by such calculation of just this Bethe equation, they not calculate, but they say us something about the following. Okay, so this is the space of functions which are 0 on a set of solutions of Bethe equation. And if we are happy with this hard proof in general, then this quotient is just space of function on a solution of Bethe equation. Yes, and no, in general, again, it's a big problem to prove something here, but at least, well, what is happening in the example? In the example happening the following, that, well, I said, for example, that if you take Mark-Magon representation And it corresponding, anyway, it's corresponding to a case d equals 0. If I factorize this by this without subtracting t term, p is 0, then the quotient is, so in this case, this part is also some space of rational functions which are 0 on some set. And as I said, for p it is really a little bit more complicated, but actually what is true? That there's such function as 0 if you these zeros are labeled by plane partition. If I take, I explain, if I take plane partition, then I can write down the set of zi, which are what? I have plane partition, zi corresponding to a box, which box have coordinates alpha, beta, gamma, yes, and then I can put y times q1 alpha, q2 beta, q3 gamma, and take all so many, so it will be z. I have as many numbers as I have boxes in my diagram, and this is what's happening if t equals 0. No, I started.
A simple question. Why it is better on that? What you solve with respect to integral system?
Well, no, let me finish this, what I want to say. Then, now, suppose p becomes, no, p has to be small, but not necessary, but suppose it is small, then we have such system of equations, and we can try to solve it. And the solution of this equation, in this case, we take this set of points, which corresponding to a plane partition, and it starts to move depending on p. And so better equation for a small p, if you write down like this, it is as many solutions. As plane partition, and they are corresponding to a basis of eigenvectors of some integrable system. And so what you ask?
But on that is used to construct eigenfunction for certain Hamiltonian.
No. Well, it is true. But first of all, we are talking, no, if you want to construct eigenfunctions, it's also possible, but we are talking only about eigenvectors.
But again, in the analysis of Bethe on that equation, there is very, very delicate case. Even in the classical story, it was completeness of Bethe on that problem, and here there are a lot of additional solutions to Bethe on that equation. So
No, it is.
It is proven that it is the same number of plane partition, number of zeros to solution to this Bethe on that equation, the same as the number.
No, surely not. Surely not. What can we see that Bethe equations have solutions,
yes,
which are corresponding, which are in a limit, which they are going to this special solution, which are arranged by plane partition. And no, about completeness, no, it's usual situation. Completeness, in completeness, for example, for Vermar representation with generic parameters is not big problem. And this is same story is here. If something is generic, then we can prove something. And because this situation cannot be simpler than usual one, then all questions which we have here, they remaining in this case. The only, no, for me at least, when I understood such kind of story, such way to get that equation was new. But that you realize, but this can be applied not only for this case, for Euro-affine algebras and for toroidal algebras, and any algebras where shuffle language can be used, such at least such approach we can do and get. No, Bethe and that equation always looking like this. And the reason in this case why it is happening, this is because we just calculate the support of the quotient, the support where the function here becomes 0. And no, my lecture is almost over, and I wanted to explain this, and I did it, but no, in this case it's a very technical problem, but in the very beginning of my lectures, I just said that such kind of approach can be used for the diagonalization of KBV. And it is really true, but it means that we need to have this algebra consider some special representation of it, and then send parameters Q1, Q2, Q3 to 1. And to do it, it's not easy, but you know, actually very complicated. But it is possible. In the limit you find integrable system which will be precisely KDV. Therefore, we can diagonalize, diagonalize in the sense what the meaning of diagonalizing is what? By the way, it is maybe also reasonable to say that our space now, which we are living, it is the space of regular functions, and this is some realization of representation. Yes, and operators there, for example, acting through these matrices, business through these operators, and so on. Yes. And no, because it is regular functions, if we have solution of that equation, say, then I can take function and substitute function to Z1 and so on ZA. And it gives me function on this space. And this function on this space will be eigencovariant. So from this point of view, a little bit in non-explicit way, it has, we have also the construction of eigenvector. But this construction is how much this is explicit is the question. But this is the same story, how much explicit the formula for McDonald's polynomial. And from this point of view, McDonald's polynomial is just set of points which are organized in partition. And you have some function and you substitute it there, and this function is eigenvector. It means that this is Macdonald's polynomial. Yes, and if you have to write down, if for Macdonald's polynomial, from this you can get some explicit formula or semi-explicit. But as a construction of eigenfunction function in general, I do not know how much this is good. Well, maybe I have 5 minutes and maybe I can stop, but I will not and say only one last comment, which is just interesting, but maybe, well, when, let us return back. When I explained about this shuffle algebra, I said, well, that we have generators EI and some kinds of relations, and then we have E0, and then we have E1, E minus 1, and so on. I explained it by maybe 2 different ways, and I just mentioned, and I said that we get commutative algebra inside shuffle. And if we take a representation and look how this representation, which I did not explain actually, but if you look some representation and look how these operators are acting here, you can get Macdonald's operator from there. So the commutative algebra in P equals 0 limit, it is just this. And the question is what is happening if I insert P. How to understand what is happening in this. No, this is from the point of view of constructing commutative algebra in terms of generator of this shuffle algebra, it's rather explicit. Some brackets and so on. The fact is, and it's an interesting thing, that if I introduce P, then the situation can be described by the following way. Well, shuffle algebra here, defined with help of function Q1 minus Q1 is 2, Q1 minus Q2 is 2, and Q1 minus Q3 is 2, and this we divide by Q1 minus Q2 Q. Yes, and if you want to deform it by P, one way to do it to deform shuffle algebra. And for this, we have to take each U1 minus Q2 and replace it by theta function. By no time to explain what does it mean, but a little bit unprecise, it means that anything like this we replace by product. Just this, it has a big sense, but nevertheless we have to do something like that. And theta function are constructing more or less by this way. Now first of all, we can do it, and this is just, I claim this. And second, no, it can be understood as a deformation of this algebra. And even if you do it, it is not so easy to understand what we get, because in this case, shuffle algebra works with Laurent polynomials, but now it's a function of how to say it is some problem. It is several ways to answer, but at least it is a serious question. Anyway, but by this way we get some algebra with deformed generator EI, and we can deform not only algebra but representations also. And for example, the 0 tilde gives me starting point of some integrable system. So before this 0 it was first gives us first McDonald's operator, but now it gives us next one will not be like this, it was wrong. But it will, nevertheless, it will be something, and it will be, actually it will be a sum of the alpha minus alpha with some coefficient. Alpha belongs to me. Yes. And it will be next element. From this system, in some sense it is this, at least it is, but very unprecise. Wait. So we can construct such kinds of operators, and it is true that all what we get by our business, either by projection operators or using this hermetic, is this. It is this integral. So, because of, maybe it is some reason for that, but I want to say that the elliptic deformation can be constructed by this way. And I have some questions which I want to think about. And this question I can only formulate. Well, I tried to explain maybe in my second lecture that shuffle algebra can be cooked from key theory of JLN, because JLN gives us symmetric polynomials, and then we calculate product. It will be, after some adjusting, it gives us a shuffle. I explained something about Grassmannian algebra and so on, but this is rather standard in a whole theory business and so on. But if you want to get elliptic version of this, it is more or less evident what to do. You have to replace this to affine algebra. And it is natural to take the theory of this, and then, it is possible to take integrable representation to start with and calculate. It is possible to invent some induction procedure and get some algebra. Yes, and what I only want to say is it is very close to what is going on here. But precisely I do not know. And even in non-deformed case, geometrical meaning from this point of view, of this integrable system and things like that. No, it is possible to speculate, but actually I don't know how to say it. It is also a good question to understand. For any geometrical point of view, it surely is. Okay, now I stop.